Welcome to another episode. Before we begin, take a moment to comment where you're listening from and what time it is there. I always love seeing how this quiet exploration connects people across the world. Now let's set the scene. For most of human history, the night sky looked fixed, a tapestry of light so still that any movement felt extraordinary. A comet streaking by, a meteor flaring for a heartbeat. But in 2017, astronomers saw something that changed how we understand the space between the stars. A visitor. Not from our solar system, but from another. ʻOumuamua, the first interstellar object ever observed passing through our cosmic backyard. 2 years later came Borisov, a second traveller, icy and active, like a wandering comet that had lost its home. And now, in 2024, the third has arrived. They've named it 3I Atlas, the third interstellar object ever confirmed, a small, pale traveller on a long, dark road between suns. There's something poetic about the idea of interstellar drift. Imagine a fragment of rock and ice, born around a star that might have burned out long before humans learned to count the stars at all. Cast off from its parent system by gravity or collision, it drifts for millions, maybe billions of years, through the cold, quiet gulf that separates one star from another. No sunlight, no orbit, only motion and memory. And then, by chance, its path brushes ours. For a brief moment, this tiny wanderer enters the domain of our sun, the same sun that rules the planets, the comets, and the dust around us, the same light that warms Earth and carves shadows through our days. The interstellar object brightens, not because it's alive, but because for the first time in ages it's seen by someone. That, in essence, is 3I Atlas, a flicker of something foreign passing through our sky for a moment and then gone. To appreciate how rare this is, it helps to remember just how empty space truly is. Between our solar system and the nearest star lies more than 4 light years of near-total void, 40 trillion kilometers, or about 25 trillion miles of almost nothing, a cosmic desert. In that vastness, even the fastest spacecraft humanity has built, Voyager 1, would take over 70,000 years to reach the next star system. Now, imagine a rock, perhaps 100 meters across, a few hundred feet, ejected from its birthplace around another sun, wandering this desert for millions of years. The odds of it ever passing close enough to our solar system to be seen are astronomically small, and yet, in just a few decades of modern observation, we've seen 3. The first, ʻOumuamua, was discovered in 2017. It moved too fast to have come from the outer reaches of our own solar system, and its path, hyperbolic, open-ended, proved it came from beyond. It was oddly shaped, elongated or perhaps flattened, and it accelerated slightly as it left, as though being pushed by something unseen. Its composition puzzled scientists. It wasn't quite a comet nor an asteroid, but something in between. Then, in 2019, 2I/Borisov appeared. More typical, a clear comet with a coma and a tail, streaming gas and dust as it approached the sun. It looked like comets from our own system, but with subtly different chemistry, richer in carbon monoxide, hinting at a colder birthplace. Now, 3I Atlas, discovered on April 18, 2024, by the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes scanning the sky for objects that might one day strike Earth. It was found by accident, not because someone was searching for interstellar travelers, but because humanity is finally watching the sky carefully enough to catch them. At first, 3I Atlas seemed ordinary, a faint blur of light moving steadily against the stars. But its orbit told a different story. Its trajectory wasn't closed, like the ellipses of planets or the long loops of comets bound to our sun. It was open, hyperbolic, meaning it had come from outside the solar system and would never return. When astronomers calculated its incoming speed, they found it was moving at roughly 26 kilometers per second relative to the sun. That's about 58,000 miles per hour. far too fast for any local comet to have been perturbed from the Oort cloud. Its path cuts through the plane of the planets at a steep angle, as though it's a stranger passing through a crowded room, unaware of the order we call the solar system. That's how scientists knew this was not one of ours. There's something strangely intimate about watching an interstellar object. Unlike the distant galaxies we see through telescopes, vast but unreachable, these are visitors in motion. They pass through our home, share our sunlight for a few brief months or years, and then move on. They remind us that the universe isn't a series of isolated systems, but a web of connections, gravity tossing fragments of one world into the sky of another. Each interstellar object is a messenger, a physical letter from a place we will never see. For billions of years, rocks have been exchanged between stars. Planetary systems, especially in their chaotic youth, fling out debris during the violent birth of planets. Most of that material drifts forever through interstellar space, dark, frozen, anonymous, but every once in a while, one crosses paths with a star like ours. It's been happening since before Earth existed, but until recently, we simply couldn't notice. The technology to detect something so small, faint, and fast didn't exist. Think of how thin the odds are. The sky is vast, and 3I Atlas is barely 100 meters wide. If our telescopes had been pointed slightly elsewhere, we might never have known it passed through, but we did see it. And now, it's part of our shared cosmic story. Each of these discoveries feels like a deepening of perspective. ʻOumuamua showed us that space between stars isn't empty. It's alive with fragments. Borisov confirmed that comets, with their icy breath, are not unique to our system. And 3I Atlas, the quietest of the three, whispers something subtler, that we're now capable of noticing these whispers at all. It's a triumph of technology and patience. The Atlas system, based in Hawaii, was designed as an early warning network to find asteroids that might one day strike Earth. It scans the whole visible sky several times each night, comparing new images with previous ones to detect anything that moves. When 3I Atlas appeared, its movement didn't fit the pattern of a near-Earth object. The software flagged it for follow-up, and soon, astronomers around the world were tracking it, confirming its speed, orbit, and most importantly, its origin. Its name reflects both its lineage and its discovery. 3I for the third interstellar object, Atlas for the system that first saw it. To some, it might seem just another rock, but to astronomers, it's a window. Each of these interstellar visitors carries within it the chemistry and structure of another solar system, a frozen sample from an alien disk of gas and dust that once circled another sun. We may never touch it, but by studying its light, the way it reflects and absorbs, we can infer its makeup, whether it's rich in carbon dioxide, whether it carries silicates or metals, whether it's a shard of a planet or a crumb of a comet. It's like trying to learn about a distant culture from a single relic that washes up on our shore. The more of these relics we find, the more complete our understanding becomes. It's possible that every few decades, perhaps even every few years, such travellers pass through our system unseen. With new wide-field surveys and telescopes like Vera Rubin coming online soon, we might detect many more. But for now, 3I Atlas is the only one in our reach, a momentary guest in the sunlight before fading into the dark again. There's something almost melancholic about its journey. It was born in chaos, perhaps when planets collided, or when a gas giant's gravity flung smaller bodies into interstellar exile. It has wandered ever since, cold and silent, untouched by any sun for millions of years. Now, for a brief time, it's illuminated again. We see it, measure it, wonder about it, and then it will continue, leaving us behind just as it left its original home. If you could ride along with it, you'd see stars drift by like slow lanterns. The sun would shrink into a pale dot until even that disappeared. The next stop might be another star system, maybe in a million years, maybe never. It's not travelling to anywhere, it's simply travelling. That's what makes 3I Atlas so quietly powerful. It's a reminder that the universe isn't a set of separate stories, it's one continuous motion, a web of journeys, collisions, and brief intersections. Our sun is just one of billions, our planets one set among countless others, and even here, in the comfort of our orbit, the traces of other worlds pass through us. So as you imagine it now, a dim bluish point of light gliding beyond the orbit of Mars, heading outward, faster than anything we could ever chase. Remember that you're living in a time when humanity can finally notice such things. Not grand spacecraft or massive worlds, but a single, drifting grain from another sun. It doesn't matter that it will soon vanish. The beauty lies in the fact that we caught its reflection for a moment, that we saw something alien passing through our sky, and knew it for what it was, and that, perhaps, is enough. On the summit of Haleakala in Maui, the air is so thin and dry that it feels like the world has stepped away from itself. The stars there are sharper, steadier, points of light in a darkness that's almost physical. It was from this volcanic peak that a network of telescopes, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, opened its electronic eyes to the heavens. Its mission is simple in concept, but profound in purpose, to find asteroids that might one day hit Earth. Every clear night, ATLAS scans the sky from horizon to horizon, taking images of nearly every patch of visible space. Then it does something that human observers once had to do by hand. It compares those pictures to the ones it took the night before. Any point of light that moves, even slightly, is flagged by an algorithm for further review. In most cases, those moving dots are familiar, known asteroids, comets, satellites, the occasional airplane, but every so often, something new slips through. On April 18th, 2024, one such dot appeared. It wasn't bright. In fact, it was faint enough that only the sensitive ATLAS detectors picked it up. But when the software compared its position against star charts and previous exposures, something was off. Its motion didn't match any catalogued object. It wasn't following the usual east-west drift of main belt asteroids, or the more erratic paths of near-Earth objects. It was moving faster, and at an odd angle, cutting sharply across the ecliptic, the plane where most planets and asteroids orbit. The automated system flagged it. The data packet, just coordinates, brightness and time, was sent to the Minor Planet Center, the international clearinghouse for newly observed solar system bodies. There, other observatories received the alert. Within hours, telescopes in Chile, Spain and South Africa were aimed at the same patch of sky, confirming that the object was real and moving fast. At first, it was listed as a possible comet. It had the faint fuzziness typical of a coma, the halo of gas and dust that forms when ices sublimate in sunlight. But its motion told a more interesting story. When astronomers began calculating its orbit, they noticed that the numbers didn't fit any closed curve. Objects bound to the sun, planets, asteroids, comets, follow elliptical orbits. Even the most eccentric comets, those that travel from the distant Oort cloud, still trace long stretched ellipses that eventually bring them back. This one didn't. The data showed a hyperbolic orbit, an open trajectory, meaning it was moving too fast to ever be captured by the sun's gravity. Once it passed through, it would keep going forever. The early orbital solution gave an eccentricity greater than 1.02. That might not sound like much, but in celestial mechanics, it's everything. An eccentricity of exactly 1.0 means a perfect parabola, an object that barely escapes the sun's pull. Anything less than 1.0 is bound. Anything greater is free. 3i Atlas wasn't just visiting, it was passing through. The confirmation came quickly. Within days, follow-up observations refined the orbit and confirmed that its incoming speed, about 26 kilometers per second relative to the Sun, roughly 58,000 miles per hour, was too high for a native solar system object. Even a comet falling from the outermost Oort cloud would move slower near the Sun's distance. That speed, combined with its steep approach angle, almost 40 degrees off the solar plane, marked it as something different. It wasn't one of ours. It had come from elsewhere. Astronomers at the University of Hawaii announced the discovery publicly, giving it the provisional designation A/2024H2. Later, when its interstellar origin was confirmed, it was renamed 3I Atlas, the third interstellar object ever identified. What's striking about this moment is how quietly it happened. There was no press conference, no sudden realization that the object was alien in origin. It was simply another entry in the nightly flow of data, one that happened to stand out because of its orbital parameters. That's a very modern kind of discovery, almost philosophical in itself. In the past, astronomers like William Herschel or Clyde Tombaugh would have spent nights at the eyepiece, scanning the heavens manually. Herschel discovered Uranus with his own eyes in 1781. Tombaugh found Pluto by comparing photographic plates with a blink comparator in 1930, straining to spot the tiny movement of a planet no one had ever seen. But 3I Atlas was found by a machine, watching tirelessly, immune to fatigue or wonder. It didn't know that what it was seeing was rare. It didn't feel the thrill of discovery. It simply followed instructions. Find movement, measure light, log data. And yet, through that digital routine, humanity glimpsed something no person had ever seen before. It's almost poetic, a robotic sentinel finding poetry where it wasn't programmed to look. At first, scientists hesitated to call it interstellar. They'd been fooled before. In 2017, when ʻOumuamua was discovered, its hyperbolic orbit immediately drew attention. But it also sparked debate. Could it have been a local object nudged into escape velocity by a planetary encounter? Statistically possible, but improbable. By the time Borisov arrived in 2019, with its unmistakable cometary activity and clear hyperbolic speed, the community was more prepared. So when Atlas reported the new object's orbit, they were cautious but intrigued. By the end of April, the evidence was solid. 3I Atlas was unbound, not just gravitationally, but narratively. It belonged to no star system. Its path suggested it came from the general direction of the constellation Serpens Caput, though that doesn't mean much. Over millions of years of travel, gravitational interactions with other stars and clouds could have changed its course many times. All we can say is that it entered our neighborhood from that region of the sky, heading inward toward the sun before curving outward again, a quick hello and goodbye. In brightness, it was modest, around magnitude 17 at discovery, barely visible to mid-sized telescopes. But as it approached perihelion, its closest point to the sun, it brightened slightly, developing a faint tail. That hinted at volatile materials on its surface. Frozen carbon dioxide, carbon monoxide, and perhaps water ice beginning to sublimate. Spectroscopic observations followed. The European Southern Observatory's Very Large Telescope and NASA's Hubble Space Telescope joined the campaign. They detected emissions typical of a comet, mainly carbon-based gases, confirming that 3I Atlas was active. It wasn't a dry fragment like ʻOumuamua. It was a living cometary nucleus, exhaling under the warmth of our star. That activity gave scientists a rare chance to study alien ice, not from another planet, but from another sun. Its light spectrum differed subtly from that of solar system comets. The ratios of carbon dioxide to water and the specific wavelengths of reflected sunlight hinted at a composition shaped in colder, more distant conditions than those of our early solar nebula. In essence, we were sampling, through photons, the chemistry of another star's planetary nursery. To measure such things, astronomers use instruments capable of breaking light into thousands of individual wavelengths. Each element or molecule leaves a fingerprint, a bright or dark line in the spectrum. By comparing these to known standards, scientists can deduce temperature, composition, and even particle size in the coma. With 3I Atlas, these fingerprints spoke of a familiar yet subtly foreign world. Not so different that we couldn't recognize it, but different enough to whisper, "I wasn't born here." The object's size remains uncertain. Estimates range around 100 meters, or about 330 feet across. That's roughly the length of a football field. At that scale, it's small enough to escape detailed imaging, even with powerful telescopes, yet large enough to carry complex ices and minerals. The fact that we could detect it at all is remarkable. Space is vast, and such objects are few. If each star system ejects billions of comets and asteroids during its early formation, and if most wander the galaxy for eons, then the solar system should be peppered with their visits. But they're so faint that until recently they went unnoticed. Atlas changed that by automating the process. It's a bit like turning on a streetlight in a dark city and suddenly realizing how many insects were flying past unseen. The data from that April night still exists, a few kilobytes of numbers recording the position of a dim smudge against the Hawaiian sky. From that small entry, a cascade of science unfolded. Telescopes turning, astronomers coordinating across time zones, emails and conference calls buzzing with excitement. For a brief window before 3i Atlas grew too faint, humanity pointed some of its best instruments toward it. Even as the object faded, the excitement remained. Not because it promised answers, but because it reminded scientists of what's possible. Each interstellar visitor expands our sample size of the galaxy. Before 2017, we knew only the material of our own solar system. Now, with 3 visitors, we have glimpses of 3 entirely different stellar histories. In the grand scheme, 3i Atlas will pass and be forgotten, a footnote in astronomical databases, its data compressed and archived. But for a brief moment, it stood as proof of our growing awareness. It's humbling to think that it took billions of years of cosmic wandering and just the right geometry for that object to cross Earth's sky at a time when a machine happened to be watching. If it had come a century earlier, no one would have seen it. If a cloud had rolled over Maui that night, it might have gone unnoticed forever. Discovery is often a mixture of luck, persistence, and timing. In this case, it was a meeting of the ancient and the new, a relic from another star, caught by a robotic telescope built to protect our own. The machine didn't know it had found something from beyond the sun's domain, but we do. So the next time you look up, imagine that faint, icy traveller, still moving, still following its hyperbolic path through the void. It carries no message, no intention, yet in its silence it tells us that the space between stars isn't empty. It's full of stories, drifting slowly, waiting for someone to notice. And on one April night in 2024, we did. When we speak of orbits, we usually mean circles or ovals, graceful loops bound to a single star. Planets, asteroids, and comets all obey that rule, tracing endless revolutions around the sun like dancers who never leave the floor. But 3i Atlas doesn't dance. It cuts through the room and keeps going, never to return. Its orbit is not an ellipse, but a hyperbola, one of the most elegant shapes in celestial mechanics. To picture it, imagine 2 mirrored arcs that curve away from a central focus, never meeting. A hyperbola is the mathematical shape of escape. It describes the trajectory of any object moving so fast that gravity cannot hold it. For 3i Atlas, that speed is about 26 kilometers per second, or 58,000 miles per hour, relative to the Sun. To put that in perspective, that's more than twice the average speed of Earth as it circles our star. At that pace, you could travel from New York to Tokyo in less than 8 minutes, and yet, in cosmic terms, it's almost leisurely. A slow glide through eternity compared to the fierce velocities of light or radiation. But in the quiet arithmetic of gravity, velocity is everything. There's a number that separates the bound from the free. Escape velocity. Every massive body, a planet, a moon, a star, has one. It's the minimum speed needed to break free from its gravity forever. For Earth, that's about 11.2 kilometers per second, or roughly 25,000 miles per hour. For the Sun, at Earth's distance, it's about 42 kilometers per second, or 94,000 miles per hour. If an object moves slower than that, it will eventually fall back, tracing an ellipse or a parabolic arc. But if it moves faster, it will never return. It will slide out of the solar system's gravity well and drift into interstellar space. 3I Atlas was already above that threshold long before it neared the Sun. Its velocity, trajectory, and energy all confirmed that it wasn't one of ours. Even if every planet's gravity tried to tug it back, the combined pull would never be enough. It would slow a little, curve slightly, and then continue outward forever. In mathematical terms, astronomers describe this through orbital eccentricity, a measure of how stretched or open an orbit is. A perfect circle has an eccentricity of 0. An elongated ellipse, like a comet's, might be 0.9 or 0.99. A parabola, the edge of escape, is 1.0, and anything greater than 1.0 means true freedom. For 3I Atlas, the eccentricity was measured at 1.025. It's a small number with a vast implication. It will never come back. When plotted in 3 dimensions, its path through the solar system looks like a long, swooping curve. It entered from far above the plane of the planets, the flat disk in which most of our worlds orbit, at an angle of roughly 40 degrees. That's steep enough to make it clear that it doesn't share our system's geometry. Most comets, even those from the distant Oort cloud, approach at gentler inclines. If you could trace its path backward across the sky, it appears to have come from the direction of the constellation Serpens Caput, the serpent's head, a faint cluster of stars about halfway between Libra and Hercules. That, of course, doesn't mean it came from any of those stars. Over the millions of years it has drifted, its course would have been bent and nudged countless times by the gravity of passing stars, nebulae, or even giant molecular clouds. Space is not truly empty, it's a slow ocean of invisible forces. Even a slight brush from a distant sun can alter a traveller's path by millions of kilometres. But still, for us here on Earth, Serpens Caput marks the direction from which this wanderer entered our local space, like the point on the horizon where a ship first appears before crossing the ocean of light. Its trajectory through the inner solar system was brief and delicate. At its closest, 3I Atlas passed within the orbit of Earth, around 1 astronomical unit from the Sun, about 150 million kilometres, or 93 million miles. And that's close enough to warm its icy surface and produce faint outgassing jets of carbon dioxide and dust. Those jets, tiny though they were, slightly altered its motion, what astronomers call non-gravitational acceleration. It's the same effect that gives comets their unpredictable behaviour. As ice sublimates, gas jets act like miniature thrusters, nudging the body ever so slightly off its purely gravitational path. For 3I Atlas, these effects were mild but noticeable, proof that it wasn't just a rock, but an active cometary nucleus. Its arc bent around the Sun in a wide hyperbolic sweep, a cosmic slingshot, and then straightened again, heading outward toward the dark. By late 2024, it was already receding, dimming quickly, as it left the reach of even the largest telescopes. By 2025, it had faded beyond detection. Somewhere far beyond the orbit of Jupiter now, it continues outward, its speed barely changed, its direction unaltered. In a few decades, it will cross the edge of the heliosphere, the bubble of charged particles blown by the solar wind. Beyond that lies the interstellar medium. Thin gas, cold dust, and the radiation between stars. There, it will drift again for ages, anonymous, until gravity steers it past another sun. To understand how unusual its path is, it helps to compare it to its predecessors, ʻOumuamua and Borisov. ʻOumuamua's approach in 2017 was shallower, entering from the direction of the constellation Lyra at an angle of about 123 degrees relative to the solar plane. It moved faster, about 87 kilometers per second relative to the Sun, and it had no visible coma or tail. It was dry, inert, mysterious. It passed closest to the Sun in September 2017, zipped past Earth at 85 times the speed of sound, and was gone within weeks. Borisov in 2019 came from the direction of Cassiopeia at a lower speed, roughly 33 kilometers per second, and displayed clear cometary activity with a long tail visible in amateur telescopes. Its orbit resembled that of typical long-period comets, except for one crucial difference. Its speed ensured that it would never return. 3I Atlas sits between them, both literally and symbolically. It shares Borisov's icy nature, but moves with a calmer, steadier pace, more like ʻOumuamua's in character. Its brightness was faint, its coma modest, its duration in our skies short, but its orbit was clean, mathematically precise evidence of interstellar origin, without the ambiguities that surrounded the first two. If ʻOumuamua was the mysterious stranger and Borisov the flamboyant traveller, 3I Atlas is the quiet observer, slipping through unnoticed, almost modest in its passage. Astronomers often visualize these interstellar trajectories in heliocentric coordinates. Imagine the sun at the center and each object's path drawn in color. ʻOumuamua's line cuts sharply across the inner solar system, tilted dramatically, intersecting the orbits of Mercury and Earth. Borisov's path swoops more gently, crossing between Mars and Jupiter. 3I Atlas enters from above the plane, loops near Earth's orbit, and exits below, a fleeting arc, like a pebble skipping once across the surface of a pond. Each path, when overlaid, reveals something beautiful. Our solar system as a stage for brief encounters. 3 travellers, each from a different direction, each telling a different story of the galaxy. ʻOumuamua, the fast and dry fragment, might have come from the disintegrating disk of a red dwarf. Borisov, with its abundant ices, likely from a cold outer region of a solar system still rich in volatiles. And 3I Atlas, whose chemistry we'll explore later, seems to have come from somewhere in between, perhaps a system with moderate warmth and a balance of dust and ice. Together, they form a tiny sample of the Milky Way's diversity, a physical record of worlds we may never see. The precision with which we can trace these trajectories is astounding. From a handful of images, each just points of light on a CCD sensor, astronomers derive a complete orbital solution: speed, inclination, perihelion distance, eccentricity, argument of periapsis. These are the celestial fingerprints of a traveller's path. For 3I Atlas, the calculations were performed by observatories around the world and compiled by the Minor Planet Center. By the end of May 2024, its path was fully mapped. The data confirmed what intuition had already whispered. This object was born under another sun, in another time, and though we know its speed and direction, its origin remains uncertain. Tracing its motion backward over millions of years is like rewinding a film through smoke. Gravitational perturbations, even tiny ones, accumulate, blurring the trail until it becomes unknowable. Some estimates suggest that 3I Atlas has been wandering the galaxy for tens or even hundreds of millions of years. It may have been ejected when its parent star was still young, when planets were colliding and migrating in a violent dance. In that sense, it's a fossil of another world's creation, a piece of debris thrown into eternity. If you could have followed it from the moment it entered our solar system, you would have seen a serene, deliberate motion. No sudden turns, no erratic zigzags, just a smooth curve dictated by gravity and time. As it approached the sun, the solar wind brushed against it, warming its ancient surface, awakening faint jets of vapor. Those jets curved its tail slightly, aligning it away from the sun like a whisper of light. Then, as it passed perihelion, its closest point, it began to slow, turn, and accelerate outward again. The whole encounter lasted less than a year, a cosmic blink. Astronomers sometimes speak of the interstellar flux, an estimate of how many such objects pass through the solar system each year. Before ʻOumuamua, that number was theoretical. Now, with 3 confirmed sightings in less than a decade, we know that the galaxy is full of them. Statistically, there may be thousands of interstellar bodies passing through our system at any given time, most too small or too dark to detect. They are, quite literally, the messengers of the stars. silent ambassadors drifting through shared gravity. Each one's trajectory is a line in a grand cosmic weave, intersecting our small circle of light for a fleeting instant before continuing on. And for all our equations and simulations, there's something deeply human about tracing that line. We chart its path, measure its speed, compute its eccentricity, but what we're really doing is following a story that began in another sky and for a brief moment crossed ours. If you could stand outside the solar system and watch it unfold, you'd see our sun glowing faintly in the center, encircled by the planetary rings of dust and rock. Then, from a distant angle, a dim speck approaches, the size of a mountain, yet nearly invisible. It sweeps through the plane of the planets, curves once, and departs. No fanfare, no collision, no trace, but a faint tail of dust dissipating in the light. That is 3i Atlas's journey, the path of a traveller who asks for nothing, leaves nothing, and yet reminds us how connected we are to the wider cosmos. Because, in the end, gravity is the universe's handwriting, and every orbit, every curve, every hyperbolic line is a sentence in the story of motion. And for one fleeting paragraph, 3i Atlas wrote itself across our sky. When astronomers first pointed their instruments toward 3i Atlas, they weren't expecting much. It was faint, small, and already speeding away by the time it was discovered. But light, even faint light, carries memory. Within those few photons, there are clues to an object's origin, its temperature, and even its past. Across the world, telescopes turned toward it: the Hubble Space Telescope, the James Webb Space Telescope, JWST, and several of Earth's largest ground-based observatories, from the Very Large Telescope in Chile to the Subaru Telescope in Hawaii. Together, they caught one of the quietest, most distant chemical fingerprints ever recorded from an interstellar visitor. And the message was clear: 3i Atlas was alive. Not alive in a biological sense, but active, a body releasing gas and dust into space. A comet. That simple fact, activity, already made it distinct from one of its predecessors. When ʻOumuamua passed through the solar system in 2017, it baffled astronomers by doing the opposite. It remained silent, dry, with no visible tail or coma. It was more like an inert shard than a comet. Yet curiously, its motion showed a faint acceleration, as if pushed by something: sunlight, outgassing, or something else entirely. The result was confusion and fascination. Some scientists proposed that it might be made of exotic hydrogen ice or nitrogen ice, others that it was a fragment of a destroyed planet's crust. A few even suggested something artificial, but 3i Atlas behaves more like 2I/Borisov, the second interstellar visitor discovered in 2019, unmistakably cometary. Borisov had a bright coma, a clear tail, and emitted gases in abundance: carbon monoxide, water vapor, and cyanide. It looked and behaved much like the comets native to our own solar system, only slightly richer in volatile ices. 3i Atlas sits between these two extremes. Where ʻOumuamua was dry and Borisov exuberant, Atlas is quietly alive, not blazing with activity, but unmistakably venting gases and dust as it nears the sun. When JWST's instruments analysed its infrared spectrum, they found a signature that told a clear story. The coma, the glowing cloud surrounding the nucleus, was rich in carbon dioxide, CO2, with faint traces of dust grains reflecting sunlight. That might sound ordinary, but it's telling. Most solar system comets display a mix of water vapor, carbon monoxide, and carbon dioxide in varying ratios. The balance between them depends on how and where the comet formed. Water ice condenses closer to a star, while carbon monoxide and carbon dioxide freeze much farther out, in colder regions of a protoplanetary disk. 3I Atlas's dominance of carbon dioxide suggests that it was born in a colder system, or at least in the outermost frigid zone of one, far beyond the frost line where water turns solid. That places its birthplace in the same kind of region as our Kuiper belt or Oort cloud, where icy bodies form from pristine, ancient material left over from a star's creation. It's the kind of chemistry that whispers of deep time, of slow formation under the dim glow of a distant sun, in temperatures so low that carbon-based molecules froze out of the gas phase and became part of the ice. Hubble's ultraviolet and visible light data complemented Webb's infrared findings. It revealed a faint, diffuse halo around the nucleus, about 10,000 kilometers wide, roughly 6,000 miles, made of sunlight reflected by dust grains. The brightness and colour of that light allowed scientists to estimate the reflectivity or albedo of the material. 3I Atlas turned out to be dark, very dark, reflecting only a few % of the sunlight that hit it. That's typical for comets, which are covered in a thin crust of complex organic compounds. The residue of carbon molecules cooked and altered by radiation over billions of years. It's the same stuff that coats our own comets and asteroids, tar-like, rich in carbon, absorbing nearly all light. The nucleus itself is estimated to be about 100 meters across, roughly 330 feet, about the length of a football field. That makes it smaller than most long-period comets, which often span several kilometers. It's a speck, really. A grain of dust on the scale of a solar system, and yet even that is enough to produce a visible coma when warmed by the sun. Through spectroscopy, the art of turning light into data, scientists identified a few more clues. The gas around 3I Atlas emitted light at wavelengths associated with carbon dioxide and carbon monoxide, with faint but notable signals from dust-scattered sunlight. But there was a curious absence, very little water vapour. In our solar system, water usually dominates cometary outgassing. As comets approach within about 3 astronomical units of the Sun, roughly the distance of the asteroid belt, the sunlight is strong enough to vaporise their water ice, releasing plumes of gas and dust. For 3I Atlas, however, the dominant gas was CO2. That means that much of its water may have remained frozen, or that its outer layers were so cold that the carbon dioxide sublimated first, creating the observed coma. This ratio, high CO2, low H2O, has become one of the defining traits of 3I Atlas. It's as if it carries the chemical fingerprint of a world more distant, colder and older than our own. When compared with Borisov, the difference is striking. Borisov's tail was rich in carbon monoxide and cyanide, with a water-to-co ratio not too far from the comets of our solar system. It likely came from a star-forming region similar to our own, perhaps a cold red dwarf surrounded by a thick, icy disk. 3I Atlas, on the other hand, appears less wet, less eager to release vapour. It's colder in character, an introvert among comets. ʻOumuamua, of course, sits at the opposite end of that spectrum. No gas, no dust, no coma, just a strange acceleration, a tumbling motion and a reddish colour possibly caused by space-weathered organic material. Where Borisov and Atlas wore their activity proudly, ʻOumuamua remained enigmatic, almost stoic, an emissary of silence. If we arrange them as a trinity, they tell an evolutionary story. ʻOumuamua, the dry fragment, like an ancient rock stripped bare by eons of radiation. Borisov, the icy traveller, exuberant and full of chemical youth. Atlas, the quiet hybrid, icy at its core but restrained. A subtle voice between the two, each one a different type of interstellar memory. The dust particles around 3I Atlas were small, submicron in size, inferred from how the light scattered. That suggests gentle outgassing, with gases slowly carrying fine grains into space rather than blasting them out in jets. It's like comparing a whisper to a shout. Borisov had the loud, dusty tail of a comet in full cry, while Atlas released its material softly, steadily, almost delicately. This subdued activity could be due to its size, A nucleus only 100 meters across has very little surface area, and sunlight can penetrate only so far. If most of its outer shell had been hardened into a crust of radiation-processed organics, then only a few pockets of volatile ice would be left to sublimate, forming localized jets. That would also explain the faint, uneven coma, a ghostly shell rather than a bright fan. To the telescopes tracking it, it looked like a small smudge of light, its brightness fluctuating slightly as it rotated, as if breathing slowly. Colour is another subtle clue. Hubble's photometry showed that 3I Atlas had a reddish tint, similar to many trans-Neptunian objects in our own system. This hue likely comes from tholins, complex organic molecules produced when radiation interacts with carbon-based ices like methane and ammonia. Over millions of years, these molecules build up a dark, rust-coloured coating, turning once white ice into reddish rock. ʻOumuamua had the same coloration. Borisov, slightly less red, seemed fresher. Its outer layers perhaps younger or less processed. But in all three, that reddish tone links them to the same chemistry, the universal carbon chemistry that runs through the galaxy like a quiet refrain. It's a comforting thought. Even across light years, the building blocks of life are everywhere, weathered by time into the same cosmic palette. There's a quiet elegance in how much we can infer from so little. From a point of light no brighter than a candle seen from 1,000 kilometers away, scientists can deduce what elements it carries, how reflective it is, how quickly it rotates, and even what kind of sunlight it has absorbed over millions of years. Every spectrum, every image is a postcard from elsewhere. 3I Atlas's postcard reads something like this: I was born in the cold. My surface is red with age. I carry carbon and dust, the same dust you walk upon. I breathe faintly when warmed by a sun, yours this time. And then, I sleep again. Its faint breath of carbon dioxide carries more than chemistry. It carries a story of cosmic recycling. The carbon atoms in its gas could once have been forged in a dying star, scattered into space by a supernova billions of years ago. Those same atoms became part of a molecular cloud, part of an icy disk around a newborn sun, part of this small, fragile traveller, and now they've returned to light for a moment in our sky. In that sense, 3I Atlas is a reminder that every bit of matter, no matter how cold or silent, is part of an unbroken lineage of transformation, from stardust to comet, from comet to vapour, from vapour back into the cosmic sea. Its chemical portrait is still incomplete. JWST's data is being refined, and more detailed analyses are expected to reveal additional compounds, perhaps methanol formaldehyde or other organic molecules. If confirmed, that would make 3I Atlas another link in the chain of evidence that the raw ingredients for life are scattered liberally across the galaxy. Each new interstellar visitor expands that evidence. Each tells us that chemistry doesn't stop at the edges of a star's light. It continues quietly in the dark. And though we may never know which star birthed this fragment, we now know a little of its story. It was formed in cold, carbon-rich dust, wrapped in red organics, exhaling a faint breath of CO2 as it basked briefly in our sun. From 100 meters of frozen stone, we've learned something profound. That the galaxy's materials are shared, familiar, universal, and somewhere out there, another fragment like it is already on its way, drifting silently between suns, waiting for the right geometry, the right alignment, the right moment for us to notice. For now, though, 3I Atlas fades once more into the dark, a grain of carbon and ice, carrying within it the echo of an alien sunrise. So far, we've followed 3I Atlas on its silent voyage through the solar system, seen the faint trail of its outgassing, and caught hints of the alien chemistry etched into its icy skin. But 3I Atlas is not just a curiosity on its own, it's part of a pattern, the third note in a cosmic chord that began just a few years ago. To understand its place, we have to look back at the two that came before it. ʻOumuamua and Borisov, and the questions they left behind. The story begins in October 2017 with a small object racing through the inner solar system at a speed that made no sense. It was first spotted by the Pan-STARRS telescope, also in Hawaii, and at first it seemed like an ordinary asteroid. Its trajectory, though, gave astronomers pause. It was moving at 87 kilometers per second relative to the Sun, about 195,000 miles per hour. Far faster than any object bound to our star could move. Its orbit was open, hyperbolic. That meant it was unbound, passing through the solar system once and never returning. The object was named ʻOumuamua, a Hawaiian word meaning scout or messenger from afar. And indeed, it was the first confirmed interstellar object ever observed. For the first time in human history, we were watching something that had formed around another star, a fragment of a foreign world, gliding through our skies. ʻOumuamua was small, maybe 100 meters long, though its exact shape was impossible to determine. It didn't reflect much light, making it difficult to study. Still, the observations we did get were enough to cause years of debate. As it tumbled through space, the way its brightness changed implied an extreme elongation, either a cigar-like shape, perhaps 10 times longer than it was wide, or a flattened pancake-like geometry, spinning end over end. For months, scientists tried to model its motion, but something didn't add up. As it left the inner solar system, its path began to deviate slightly from what gravity alone could account for. The deviation was tiny, just a few 10,000ths of a meter per second, but real. This non-gravitational acceleration usually occurs when comets release gas from their surfaces, creating a tiny thrust as they vent material into space. But ʻOumuamua showed no coma, no tail, no dust, no visible activity at all. It was as though it was being pushed by some invisible force. Most scientists proposed mundane explanations, outgassing of hydrogen or nitrogen that might have been invisible to our telescopes, or radiation pressure acting on an object with an unusually low density. But one voice, and later a whole debate, made the story famous beyond astronomy circles. In 2021, astrophysicist Avi Loeb of Harvard University published a provocative hypothesis that ʻOumuamua might not be a natural body at all, but an artificial object, perhaps a fragment of alien technology, like a solar sail propelled by starlight. He argued that the combination of its odd shape, lack of visible outgassing, and anomalous acceleration were difficult to reconcile with natural explanations. The scientific community largely disagreed. Most considered it an intriguing but unlikely speculation, yet Loeb's idea struck a cultural nerve. For the first time, an object from another star system had passed through ours, and some were willing to ask whether it could have been made. Then came 2I/Borisov, discovered on August 30th, 2019, by amateur astronomer Gennady Borisov using a home-built telescope in Crimea. Where ʻOumuamua was silent and mysterious, Borisov was spectacular, a textbook comet. It developed a bright coma and a tail stretching hundreds of thousands of kilometers, visible through backyard telescopes. Spectroscopic analysis quickly revealed familiar components: water vapor, carbon monoxide, and cyanide. For the first time, we could directly measure the chemistry of material from another star. The results were astonishingly familiar. Borisov's ices had similar ratios of volatile elements to those found in solar system comets. It suggested that planetary formation processes are universal, that the same chemistry plays out around many stars. Borisov's speed and trajectory confirmed its interstellar nature, about 33 kilometers per second or 74,000 miles per hour. Its orbit was open, and its inclination, about 45 degrees to the solar plane, placed it on a one-time passage through the inner solar system. If ʻOumuamua was the strange, uninvited guest who left us puzzled, Borisov was the friendly neighbour who confirmed that other worlds are built from the same ingredients as ours. Then, nearly 5 years later, 3I Atlas appeared. Not as bright as Borisov, not as bizarre as ʻOumuamua, but balanced somewhere between them. It was active, yes, its faint breath of carbon dioxide forming a soft coma, but not dramatically so. Its brightness varied modestly, hinting at rotation, but not the wild tumbling seen in ʻOumuamua. Its chemistry was familiar, but subtly different, richer in carbon dioxide, poorer in water, and its behaviour followed the predictable path of a comet, without any unexplained accelerations. For scientists still haunted by the questions of the first two visitors, 3I Atlas felt like a stabilising presence, a data point that grounded the pattern. When you line up the three, their contrasts tell a remarkable story about how planetary systems work. ʻOumuamua, dry, inert, possibly once icy but long since baked by cosmic rays. Borisov, active, wet, filled with volatiles, likely ejected recently from its home system. Atlas, quiet but active, with a frozen chemistry distinct from our own comets. It's as if we've sampled three different evolutionary stages of interstellar debris, a desiccated relic, a pristine comet, and something in between, worn but still breathing. Each one reflects a different kind of birthplace, a different history of radiation, collisions, and ejection. ʻOumuamua's mystery may never be fully solved. The non-gravitational acceleration remains its most puzzling trait. In 2023, a team led by Jennifer Bergner and Daryl Seligman proposed a plausible natural explanation that ʻOumuamua might have been made of frozen molecular hydrogen trapped inside porous ice. When sunlight warmed it, the hydrogen sublimated invisibly, producing enough thrust to account for the observed acceleration without creating a visible tail. Others have argued for nitrogen ice, like the frozen crust of Pluto, chipped from the surface of a distant planet and sent drifting after a collision. Either way, both explanations suggest that ʻOumuamua's strangeness may lie not in alien engineering but in alien chemistry, ices and materials unfamiliar to our solar system but perfectly natural elsewhere. 3I Atlas supports that view. Its gases, dominated by CO2 rather than water, prove that chemical diversity among planetary systems is real. The ratios of carbon, oxygen, and hydrogen vary depending on the temperature and metallicity of the star's protoplanetary disk. In a sense, each interstellar object is a data point in a galactic experiment that has been running for billions of years. The debate over shape continues too. ʻOumuamua's light curve, its rhythmic brightening and dimming as it rotated, suggested an elongation of at least 6:1, possibly 10:1. That's extreme for any natural object. Some scientists favour the pancake model, in which ʻOumuamua was a thin, flattened shard, perhaps the fractured crust of a larger body. Others prefer the cigar model, imagining it as a long, tumbling spindle. 3I Atlas, though too faint to measure precisely, seems far more modest in shape, probably irregular but roughly spherical, like most small comets. Its brightness changes smoothly, implying rotation, but not the sharp glints of a tumbling slab. That alone suggests a more ordinary formation. Not an exotic shard, but a rounded remnant of an icy core. It's comforting, in a way. After years of speculation about alien sails and hydrogen icebergs, 3I Atlas reminds us that sometimes a comet is simply a comet. Yet in other ways, Atlas complicates the story. Its composition is strange enough to expand our definition of what ordinary even means. By showing strong CO2 emission and very little water, it hints that our solar system's balance of volatiles may not be universal. Perhaps around other stars, the frost lines, the boundaries where different ices condense, lie in different places. Perhaps comets there are built not from water and dust, but from carbon dioxide and methane. In that sense, Atlas is an ambassador from a colder, darker kind of world. If we could trace its origin, we might find a red dwarf star surrounded by icy rubble, orbiting in a region where sunlight never reaches above -200 degrees Celsius. It's humbling to realize that such places are common, and that fragments from them occasionally drift into our warm neighborhood, carrying their alien chemistry across the light years. Each of these interstellar visitors has expanded our vocabulary for what's possible. Before 2017, the idea of detecting one at all seemed nearly impossible. Now astronomers are preparing for the next. The Vera C. Rubin Observatory, with its massive 8.4-metre mirror and nightly all-sky surveys, is expected to find several interstellar objects every year once it begins full operations. Each discovery will sharpen the picture: how often they arrive, what they're made of, how they behave in sunlight. If we're lucky, one will appear soon enough, bright enough and close enough to reach with a spacecraft. Projects like ESA's Comet Interceptor or NASA's Interstellar Probe are already being designed with that possibility in mind, ready to launch toward the next messenger that crosses our path. But even without such missions, the three we've already seen have transformed our sense of belonging in the galaxy. They've shown us that matter from other suns flows through our solar system, not metaphorically, but literally, that the gap between stars isn't an unbridgeable void, but a place of exchange, where fragments of distant worlds drift slowly between gravitational wells. ʻOumuamua told us that alien fragments exist. Borisov showed us that their chemistry is familiar, and 3i Atlas has revealed that even in that familiarity there is endless variety, subtle differences that hint at the diversity of worlds we've yet to see. It's easy to romanticize these travelers, but their reality is even more astonishing. Each one is a physical piece of evidence in a cosmic story of motion, an experiment billions of years in progress. They're not just visitors, they're proof that planetary systems are porous, that stars exchange material the way trees exchange pollen, spreading the seeds of chemistry across light years. When we look at 3i Atlas, faint and distant, we're looking at something older than any civilization, older than Earth itself. We're watching the galaxy breathe, in and out, as matter circulates from one star's birth to another's death. And maybe, somewhere in that circulation, there are the ingredients of life, drifting, surviving, waiting. If 3i Atlas settles anything, it's this: the extraordinary can be natural. It reminds us that mystery doesn't always mean miracle, but it also deepens the wonder, because natural processes left to work for eons can produce shapes, speeds, and chemistries stranger than anything we could imagine. Where ʻOumuamua challenged our assumptions and Borisov comforted them, Atlas balances both, a quiet whisper that says, "There's still more to learn, and I am not the last." We've watched 3i Atlas pass through our solar system, a faint comet from another star, its pale glow barely reaching us before fading into night. But what if that brief encounter was more than a spectacle? What if, hidden in its trail of dust and ice, is a record of something greater, the story of how worlds are made and how they connect? Because every interstellar object, every wanderer like 3i Atlas, is more than a rock in motion. It's a time capsule, a frozen sample of a foreign sun's history. And to study one is to glimpse the architecture of another planetary system light years away. To understand what 3i Atlas tells us, we have to start at the beginning. Not of its journey, but of all planetary systems, including our own. When a star is born, it forms from the collapse of a dense cloud of gas and dust, a molecular cloud, often dozens of light years across. As the cloud contracts under gravity, it spins faster, flattening into a disk around the forming star. This disk, called a protoplanetary disk, is the workshop of creation. Dust grains collide and stick, pebbles gather into boulders, boulders merge into planetesimals, the seeds of planets. It's a violent, chaotic time. The young star spits out bursts of radiation and solar wind. The newborn planets tug on each other gravitationally, shifting orbits, scattering debris. Many smaller bodies are thrown outward, flung into the cold, distant reaches of the system, or ejected entirely into interstellar space. That's how most interstellar objects are born. They are the exiles of planet formation, fragments that never found a stable home, cast adrift to wander between stars. Some are icy, like 3i Atlas and Borisov. Others may be rocky or metallic like ʻOumuamua. Each carries within it the elemental composition of the nebula it formed in, the isotopic fingerprint of another sun. When astronomers say that such an object is a time capsule, they mean it quite literally. Inside its nucleus, beneath the irradiated crust and layers of ancient dust, lie ices and minerals that have not changed for billions of years. No sunlight has melted them, no atmosphere has eroded them. They are pristine samples of the chemistry that once surrounded their parent star. Imagine taking a core sample from another world's formation zone, an untouched fragment of a disk that spun around a foreign sun when the galaxy itself was younger. That's what interstellar objects like 3I Atlas represent. And because they come from different stars, each one tells a slightly different version of the same cosmic recipe. One of the first things scientists look for in such bodies are isotopic ratios, the proportions of different forms of the same element. Hydrogen, for instance, comes in two main isotopes: ordinary hydrogen, a single proton, and deuterium, a proton and a neutron. The ratio of hydrogen to deuterium in a comet's water ice tells us about the temperature and conditions in which that ice formed. In our own solar system, comets from the Oort cloud tend to have higher deuterium levels, suggesting they formed in colder, more distant regions. Comets from the Kuiper belt, closer in, have slightly lower ratios. So when we study an interstellar comet like Borisov, or infer from 3I Atlas's CO2-rich composition, we can compare these ratios to see if its birthplace was colder or warmer, denser or thinner than our own early solar nebula. So far, the evidence suggests that these visitors come from systems chemically familiar, but not identical to ours. The same ingredients, water, carbon dioxide, carbon monoxide, dust, appear everywhere but in different proportions. The details matter. They tell us how each star's protoplanetary disk cooled, how its planets formed, and even what kind of light its sun emitted. Take 3I Atlas's carbon dioxide dominance. In our solar system, CO2-rich comets usually come from the farthest reaches, the outer Oort cloud or beyond, where the sun's warmth was too weak to vaporize that ice during formation. If Atlas formed in a similar region, it must have been born far from its parent star, in temperatures around -200 degrees Celsius or -328 degrees Fahrenheit or colder. The same pattern applies to its dust. The spectral slope, the way its light changes color with wavelength, shows a reddish hue, meaning its dust grains are coated with complex organic molecules. These so-called tholins are formed when ultraviolet radiation and cosmic rays interact with frozen methane, ammonia, and other hydrocarbons over millions of years. Such chemistry happens in the outer disks of young stars, the same zones where comets form in every system. So, in essence, the surface of 3I Atlas carries the signature of deep time under a foreign sun, a layer of carbon-rich varnish painted by cosmic radiation. But these aren't just curiosities about one object. They tie into something larger, the galactic exchange of matter. Every star forms from material recycled from earlier generations of stars, supernova debris, stellar winds, and cosmic dust. That means the atoms in your body, the rocks under your feet, and the gases in distant comets all share the same ancestry. But beyond that slow chemical mixing, there's also physical exchange, the swapping of solid material between solar systems. When young planetary systems are packed tightly together in stellar nurseries, their gravity wells overlap. A comet ejected from one system can drift for millions of years before being captured, even briefly, by another. Over the lifetime of the galaxy, trillions of such fragments have traded places. The result is a kind of cosmic archipelago where debris from one world can seed another, like pollen carried by an invisible wind. It's likely that our solar system has captured interstellar objects before and ejected many of its own. Some simulations suggest that our Oort cloud could contain hundreds of millions of bodies that were not born here. And likewise, there are probably countless icy fragments from the sun's youth now drifting through the Milky Way, passing other stars as silent ambassadors of our origin. This idea of galactic exchange reshapes how we think about planetary systems. They're not isolated islands, they're porous, connected ecosystems exchanging material across unimaginable distances. When you trace the path of 3I Atlas, you're looking at one thread in that web. It may have formed around a red dwarf 10 light-years away, been ejected during a chaotic planetary migration, and wandered through interstellar space for tens of millions of years before entering our sky. During that time, it might have passed near other stars, through molecular clouds, and even through regions of the Milky Way where new stars were forming. Each passage leaves a mark, cosmic rays altering its chemistry, micro-impacts chipping its surface, solar radiation reshaping its crust. By the time it reached us, it was no longer just a fragment of one star system. It was a citizen of the galaxy. The thought is almost poetic. Matter travelling between suns, carrying the memory of one world into the light of another. And perhaps, over billions of years, such exchange could spread more than dust. It could spread the building blocks of life. Scientists call this idea panspermia, the possibility that microscopic life, or the precursors of life, could be carried between planets or even between stars by natural processes. While it remains speculative, interstellar comets make the concept less abstract. They show us that material does travel between systems, that icy bodies can survive millions of years in deep space, and that organic compounds persist through that journey. If 3I Atlas carries amino acid precursors or complex organics, as some of our comets do, then it's a fragment of a chain that could, in theory, connect living chemistry across the galaxy. Whether or not life ever hitched a ride is unknown, but the traffic lanes exist. Even beyond biology, the existence of objects like 3I Atlas changes how we understand our place in the Milky Way. Until recently, we imagined solar systems as self-contained, like bubbles floating in the dark. Now, we see them as part of a galactic ecosystem, exchanging gases, dust, and debris the way ocean currents mix water between continents. If we could map the paths of every interstellar fragment, they'd look like filaments of motion weaving through the galaxy, much like the cosmic web that binds galaxies themselves, a fractal pattern of sharing and scattering. 3I Atlas, ʻOumuamua and Borisov are the first we've seen clearly enough to name, but statistically, there are likely billions of such travellers drifting right now between the stars. They are the silent couriers of the universe, slow, persistent, and indifferent to time. In a way, they also give us something we can't get any other way, a direct sample of another solar system. We can study exoplanets with telescopes, analysing their light, guessing their atmospheres, but we can't touch them. An interstellar object, though fleeting, is physical. If we could intercept one, if a future mission could fly beside it and sample its dust, we would hold in our hands material from another star. NASA and ESA have discussed this possibility seriously. Missions like Comet Interceptor or Project Lyra aim to stay on standby, ready to launch toward the next interstellar visitor. If we're lucky enough to reach one, we could measure its isotopes directly, hydrogen, carbon, oxygen, and compare them to our own. We'd know for the first time not just that other worlds exist, but what their chemistry truly is. And what 3I Atlas already hints is that, despite the distances, the universe plays with the same elements: carbon, oxygen, hydrogen, nitrogen, rearranged endlessly into new patterns. It's as if the galaxy is composing a single symphony, and each solar system is a variation on its theme. Our own Earth, then, is just one phrase. Brief, but part of the same song. When you think of it that way, these interstellar wanderers aren't just travellers, they're messengers of kinship. Each one reminds us that we are made of shared material, that the atoms in us may once have drifted in the same molecular cloud as the ones in 3I Atlas. So what does it tell us about other worlds? That they are not distant in kind, only in place. That their comets form, fracture and scatter as ours do, that their chemistry echoes ours, but with new balances, new flavours of creation, and that the universe itself is a grand recycler, turning stardust into worlds, worlds into fragments, fragments into dust again, carried endlessly by gravity's invisible hand. In 3i Atlas, we see that process frozen mid-motion, a piece of another world on its way to nowhere, stopping briefly under our sun's light. And as it moves on, it carries a trace of us too, photons from our star, particles from our wind, a whisper of our existence added to its long journey. When it finally leaves the heliosphere and returns to the interstellar deep, it will fade again into anonymity. But it won't be alone. Every such traveller carries the memory of countless others, a galaxy of shared beginnings. And perhaps one day, far from here, someone, or something, will look up at their night sky, see a faint point of light gliding by, and wonder, where did that come from? They'll never know, of course, but we might, because we've already learned to ask the same question. There are moments in science when even the clearest data seems to hum with uncertainty, when a pattern appears just faintly enough to question whether it's real or merely the artifact of our imperfect instruments. 3i Atlas, for all its measured calmness, sits squarely in that space between clarity and mystery. It doesn't display the wild irregularities of ʻOumuamua, nor the exuberant tale of Borisov, yet something about it resists easy classification. It's active, yes, but too faint to be a typical comet. It's stable in shape, but not entirely uniform in its behaviour. And just as it began to slip beyond the reach of our best telescopes, it left behind a handful of clues, small, intriguing anomalies that may take years to unravel. When astronomers first tried to measure its rotation, they expected a simple, repeating brightness curve. Most small comets rotate steadily, their spin causing periodic fluctuations in reflected light as different sides of the surface catch the sun. 3i Atlas, however, didn't follow that rhythm precisely. Observations from the Lowell Discovery Telescope in Arizona showed slight variations from one night to the next, a wobble in its brightness pattern that hinted at non-principal axis rotation or tumbling. It's a condition familiar to small bodies in space. Rather than spinning smoothly around a single axis, they rotate chaotically, like a football spiralling through the air after an uneven throw. For 3i Atlas, the tumbling seemed subtle, perhaps a slow precession caused by uneven mass distribution or small jets of outgassing shifting its spin. If true, that would suggest its surface isn't uniform. Maybe part of it is denser or coated with different ices that respond unevenly to sunlight. Such irregularities can reveal a lot. A tumbling motion means internal stresses, and stresses point to structure, fractures, layers, frozen pockets. In a sense, the way an object spins can tell us as much about its internal architecture as a direct sample. The colour of 3i Atlas also raised eyebrows. In early images, it appeared reddish, consistent with a carbon-rich surface. But later, as it neared perihelion and its coma grew more active, its colour index shifted slightly toward the neutral, more greyish, less red. It's a subtle change, barely within the margin of error, but it might mean that as new material was released from beneath the crust, we were seeing fresher ice, material that hadn't been weathered by cosmic radiation. This kind of colour evolution is not unusual for comets, yet in an interstellar context, it carries extra weight. It gives us a glimpse beneath the skin of another solar system's debris, revealing a contrast between surface and subsurface, between what time has scarred and what remains pristine. Some astronomers have proposed that the outer layer of 3i Atlas, exposed to cosmic rays for millions of years, had been darkened and reddened by organic residue, while the material beneath remained lighter, untouched by interstellar radiation. The transition, then, wasn't just cosmetic. It was geological in nature, a glimpse through time. Another feature, subtle but significant, lies in its asymmetric outgassing, the uneven release of gases and dust from its surface. Comets often vent in multiple directions, but their activity tends to peak symmetrically around perihelion, when sunlight is strongest. In 3i Atlas's case, its emissions appeared stronger after perihelion than before, and slightly lopsided. That asymmetry might mean that only certain regions of its surface were active, perhaps a single fracture line or crater acting as the main vent. Alternatively, it could hint at a thermal lag, the time it takes for heat to penetrate the crust and reach deeper ices. The sun's warmth may have taken weeks to reach pockets of carbon dioxide beneath the surface, causing delayed jets of vapour after the closest approach. The European Southern Observatory's 4S2 spectrograph detected variability in the intensity of carbon dioxide lines that seemed to support this idea. The gas emissions rose and fell irregularly over several days, like the breathing of a slow, uneven heart. All of these clues contribute to an ongoing debate. Is 3I Atlas a comet, an active, volatile-rich body, or an icy asteroid, something drier with only traces of sublimating material left? At first glance, its carbon dioxide emissions clearly mark it as cometary. But its faintness, modest coma, and low dust production don't fit the profile of an ordinary comet. Some researchers have described it as a transitional object, sitting halfway between the two categories. In that sense, it could be similar to Damocloids, extinct comets in our solar system whose ices have mostly evaporated, leaving only dark, inert shells that occasionally vent gas when heated. If 3I Atlas is one of these transitional bodies, it might represent a later evolutionary stage, an ancient comet whose once volatile layers have mostly gone, preserved only in deep, isolated pockets. Given that it has spent millions of years adrift in interstellar space, bombarded by cosmic rays and stripped by micrometeorite impacts, this would make perfect sense. What we're seeing then may be the slow fading of activity, the last breath of a once vibrant comet. Tracking these behaviours has been extraordinarily difficult. By late 2024, 3I Atlas had dimmed to magnitude 20, far beyond the reach of most amateur telescopes, and challenging even for professional observatories. At that brightness, it's not a visible object anymore, but a statistical one, existing as coordinates and error bars, faint smudges buried in noise. Even the James Webb Space Telescope, with its precision, struggled to collect useful spectra as the object receded. The problem isn't just distance, but motion. Interstellar objects move quickly relative to background stars. Long exposures blur them, and short exposures barely capture enough light to analyze. To study something like 3I Atlas, astronomers often rely on a technique called shift and stack. They predict the object's motion, then take dozens or hundreds of images, shifting each one slightly before adding them together. The faint streak of the object aligns, while the background stars blur away, a digital echo of the long exposures once made on glass plates. But even that technique has limits. The farther Atlas travels, the dimmer it becomes, until it blends back into the dark, another invisible wanderer slipping from human sight. Still, research continues. As of early 2025, several observatories have planned coordinated attempts to re-observe 3I Atlas as it moves toward the edge of the solar system. The European Space Agency's Gaia mission will track its motion against background stars, refining its trajectory. The Subaru telescope and VLT will attempt deep imaging to measure its brightness evolution and search for any residual outgassing. If successful, these efforts could answer one lingering question. Will 3I Atlas remain active as it exits the heliosphere, or will its coma fade completely once it crosses the sun's thermal boundary? That answer matters, because it tells us how resilient these interstellar travellers are, how long their ices can survive under the faint warmth of distant stars. Of course, where there are mysteries, speculation always follows. A few fringe discussions have noted the peculiar regularity of its outgassing patterns and wondered whether it might show non-random intervals, periodic bursts that could imply internal structure or resonant rotation. Some have even drawn superficial parallels to ʻOumuamua's unexplained acceleration, but so far the data remains consistent with ordinary physics. Asymmetric jets, delayed heating, and irregular tumbling can easily explain what we see. There's no need to invoke anything exotic. The reality, if anything, is more interesting than any wild theory. 3I Atlas reminds us that natural processes, working over incomprehensible timescales, can produce effects so delicate they look almost deliberate. A fragment of ice and dust, ejected millions of years ago, can move through sunlight and shadow in ways that mimic precision. Not because it's controlled, but because the laws of physics, left to act undisturbed, are themselves a kind of art. Even with all its faintness and fading trail, 3I Atlas continues to provoke careful study because it represents a data bridge between the two previous visitors. ʻOumuamua left us puzzled about how interstellar debris behaves when dry. Borisov showed what a healthy interstellar comet looks like when rich with volatiles. And now Atlas, occupying a middle ground, might reveal what happens in between, how long an icy fragment can survive in interstellar exile before becoming inert. Its subtle outgassing, faint irregular spin, and changing colour all suggest an object in transition, slowly exhausting its ancient reserves, perhaps on the verge of going dormant forever. It is, in that sense, a glimpse into the life cycle of a comet, stretched across light years. If predictions hold, by the middle of 2025, 3I Atlas will have passed beyond the orbit of Jupiter, shrinking in brightness until even the largest telescopes can no longer detect it. It will keep moving at roughly 26 kilometers per second, carrying with it the traces of its last encounter with sunlight. Somewhere beyond Saturn, it will cross an invisible boundary where the solar wind weakens and interstellar space begins. The gases it released will disperse, fading into the background plasma, their molecules broken apart by radiation. What remains will be a dormant nucleus, silent again, turning slowly in the dark. And yet, for a brief window in human time, we caught it, saw it spin, breathe, and change. In those small anomalies, we glimpsed the subtle physics of a traveller billions of years in motion. Perhaps the most profound lesson from 3I Atlas's strangeness is that the border between comet and asteroid is not a line at all, but a spectrum. Objects evolve, they lose their ices, gain crusts, fracture, and drift. They are not static categories, but dynamic beings, shaped by heat, cold, and chance. 3I Atlas may leave us no final answers, only patterns, brightness curves, spectral lines, coordinates, yet through them it speaks a universal truth, that even in silence, even in faintness, the universe is still in motion, still changing, still creating new puzzles for those who look closely enough. When an object like 3I Atlas enters our solar system, it doesn't just pass through space, it moves through the imagination of an entire planet. Within days of its discovery, observatories, space agencies, and even backyard telescopes across the globe were turned toward a single point of light, barely brighter than a pixel. It's a remarkable thing to consider. One faint speck appearing in a telescope's field can awaken a chain of scientific coordination spanning continents. At the heart of that mobilization lies a simple truth. When something truly alien passes by, we race not only to see it, but to understand it before it's gone forever. The discovery notice for 3I Atlas circulated through the Minor Planets Center within hours of its detection. The MPC, based at the Harvard-Smithsonian Center for Astrophysics, acts as the planet's central nervous system for small-body astronomy. Once the object's unusual motion was flagged, automated alerts rippled outward to hundreds of observatories and research teams. From Chile's Paranal Observatory to the Canary Islands' Roque de los Muchachos, from NASA's Infrared Telescope facility in Hawaii to the Subaru telescope atop Mauna Kea, a global relay began. Each telescope added a few more data points, precise measurements of position, brightness, and spectrum, all feeding into refined orbital models. By the following week, the international astronomical community had confirmed what the orbital eccentricity already suggested. 3I Atlas was not one of ours, and with that, the race began. The first challenge was purely practical. How do you study something that's leaving? Interstellar visitors are, by definition, fast. 3I Atlas entered the solar system at about 26 kilometers per second, nearly 60,000 miles per hour, relative to the Sun. Even by the time it was discovered, it had already passed the point of no return, inbound toward its brief perihelion swing, before slingshotting outward forever. That meant astronomers had a window of only a few months to collect all possible data, chemical, photometric and astrometric, before it faded below detectability. It was a race against the universe's clock. Observing campaigns were organized almost overnight. NASA's Planetary Defense Coordination Office issued observation requests to its partner telescopes, not because 3I Atlas posed any danger, but because its motion and composition could teach scientists how to better identify and classify future interstellar visitors. ESA, through its Near-Earth Object Coordination Center in Italy, joined in, pooling data from European telescopes to refine the trajectory. But it wasn't just agencies and professionals. Dozens of amateur astronomers, some operating small robotic observatories from their backyards, joined the effort. Their contributions were vital. Amateurs can often capture repeated exposures over multiple nights, filling in gaps between professional observing runs. These citizen scientists uploaded data to international repositories, helping track the object's faint drift across the stars. It was a quiet, collective choreography. Thousands of eyes, human and robotic, all following a single, anonymous speck. The excitement echoed a familiar pattern. In 2017, when ʻOumuamua was first recognized as interstellar, a similar global scramble had unfolded, though that one came too late for deep analysis. By the time its nature was confirmed, it was already vanishing into the outer dark. With 2I/Borisov discovered earlier in its inbound path, astronomers managed months of continuous study, even catching the comet's breakup as it neared the Sun. This time, with 3I Atlas, the response was immediate and coordinated, a sign that humanity had learned from the first two. Within 48 hours, both JWST and Hubble observation proposals were submitted and approved under rapid response protocols. Such approvals usually take months. For interstellar visitors, they happen in days. The priority was clear. We might never get another chance. Every observation had to be meticulously planned. Because 3I Atlas was moving so fast, it would drift several arc-seconds across the sky during long exposures, enough to blur its image into a streak. Astronomers compensated by tracking the object's predicted motion, effectively letting the telescope move with it. Each frame captured a still point of light, while the background stars smeared into short trails, an inversion of how we usually observe the sky. The data that came back, though faint, carried an enormous weight. It contained spectral fingerprints of carbon dioxide, faint variations in brightness revealing spin, and enough positional data to refine its orbit to within a few thousand kilometers, a precision remarkable for something already millions of kilometers away. But for some, observation wasn't enough. Within days of confirmation, engineers began asking the question that inevitably arises with every interstellar visitor. Could we reach it? The answer, as always, was complicated. At its discovery, 3I Atlas was already moving too fast and too far for any existing spacecraft to intercept. Even if a probe were launched immediately, the required delta V, the change in velocity needed to catch it, would be beyond current propulsion technology. But that didn't stop scientists from trying to model the possibilities. Teams associated with Project Lyra, an independent research initiative originally conceived to intercept ʻOumuamua, updated their simulations. Their conclusion, 3I Atlas was too far gone for a direct chase. By the time any spacecraft could be built and launched, it would be billions of kilometers away. Still, these feasibility studies weren't wasted. They tested new trajectories, propulsion concepts, and orbital mechanics that could one day make such missions possible. Ideas like solar obverse maneuvers, slingshotting near the Sun for a speed boost, or advanced solar sails capable of continuous acceleration are all being refined because of these fleeting visitors. In a sense, 3I Atlas has become another proving ground for imagination. ESA's Comet Interceptor mission, scheduled for launch later this decade, is built precisely for this kind of event. Unlike traditional missions that target known comets, Comet Interceptor will wait in space at the L2 Lagrange point, a gravitationally balanced spot about 1.5 million kilometers from Earth. There it will remain on standby, ready to depart on short notice toward any newly discovered comet, or, ideally, an interstellar one. Had 3I Atlas been detected earlier, Comet Interceptor could have been a candidate. Its modular spacecraft could separate into multiple probes, approaching the target from different angles, collecting high-resolution imagery and sampling dust. That mission will likely miss this visitor, but the next one might not escape. Meanwhile, NASA has floated conceptual missions like Interceptor for Interstellar, an extension of the planetary defense network that could launch small, rapid-response probes toward similar targets. The idea is to maintain a fleet of ready spacecraft that can adapt their trajectories once a new object is found. It's a new kind of exploration, not of fixed destinations, but of fleeting encounters. There's something beautifully human about the urgency these objects inspire. For all our technological limits, the instinct to reach, to chase, to follow, it hasn't dimmed since the first astronomers tracked a comet across the sky with nothing but a brass telescope and hope. When an interstellar object appears, it's as if the cosmos has sent us a challenge. Here is something from another sun. You have a few months to learn what you can, and humanity responds with a kind of organized panic. Late nights in observatories, rushed data analyses, emergency mission meetings, proposals submitted in record time. The entire scientific world briefly moves in sync, united by a tiny piece of rock that most people will never see. It's easy to underestimate the scale of this collaboration. Behind every image of 3I Atlas, every faint smear of light, lies an invisible network of people. Telescope operators adjusting coordinates, analysts correcting for atmospheric distortion, programmers writing algorithms to remove cosmic rays from frames, archivists uploading data to public databases so others can compare results. Each step is a small gesture of shared curiosity. As 2025 unfolds, the final coordinated campaign to observe 3I Atlas is underway. The Vera C. Rubin Observatory, with its enormous field of view, will soon begin routine sky surveys that may catch the fading trail of the object as it moves beyond Jupiter's orbit. At the same time, the Gaia spacecraft will continue refining its parallax data, helping trace the object's long-term trajectory through interstellar space. By then, it will be almost invisible, fainter than magnitude 25, buried in noise, and yet, somewhere in that faint trace, scientists will still be looking for patterns, the last flickers of reflected sunlight, the smallest asymmetries that might reveal one final clue before the darkness swallows it again. It's a race no one expects to win, but everyone feels compelled to run. That urgency says something about us. It shows that curiosity can mobilize faster than politics or profit. No government had to order the world's telescopes to coordinate. No central authority directed the amateurs who stayed up through the night to image a faint smudge of light. The impulse was instinctive, to look, to learn, to share. In that sense, every interstellar visitor becomes a kind of test. How quickly can humanity come together to understand something new? And so far, the answer has been encouraging. From the moment Atlas was spotted, hundreds of individuals, scattered across countries, languages, and institutions, worked toward a common goal, guided not by ownership, but by wonder. If we imagine a future where such cooperation deepens, where spacecraft truly stand ready to chase the next messenger, then each of these fleeting encounters becomes a rehearsal for something greater. The moment we finally reach one, sample its dust, and touch material from another star, we will have crossed an invisible boundary in our species' story. Until then, these global efforts remind us that the line between what is alien and what is human is narrower than it seems. When the universe offers us something unfamiliar, our first instinct is not fear, but fascination. In the end, the race to study 3I Atlas is less about speed and more about alignment. A rare moment when thousands of minds turn together toward the same mystery. The object itself will vanish soon enough, a silent wanderer slipping back into interstellar darkness. But for a brief moment, it has illuminated something just as remarkable. The collective heartbeat of a species still learning how to look outward. And maybe, in that shared act of looking, we're already a little closer to the stars we seek to understand. It's strange, isn't it? To think that right now, even as we go about our quiet lives, fragments of other worlds are slipping unseen through our solar system. Most are too faint to notice, too small to reflect enough sunlight to betray their passage, but they are there, drifting, ancient, silent. Statistically, there may be billions of such travellers crossing the space between stars. They don't announce themselves like comets with shining tails. They don't burn through our atmosphere as meteors. They move like whispers through the deep, brief intersections between one star's story and another's. 3I Atlas was simply one that happened to be illuminated at the right angle in the right decade for us to see. But the realization that these interstellar wanderers exist, that the void between suns is populated by relics of creation, changes something fundamental about how we see the universe. It tells us that isolation is an illusion. Every atom in every rock, every breath of air, every drop of water was forged in a star. Some in massive blue giants that exploded as supernovae, others in smaller, older suns that shed their outer layers gently into the galactic sea. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was once part of other worlds. The same fusion reactions that powered those long-dead stars created the ingredients that make up you. And now, across the galaxy, those same atoms continue their journey, forming new stars, new planets, new wanderers like 3I Atlas. When one of them passes through our solar system, it's not a visitor in the human sense, it's family. To watch 3I Atlas move across the sky is to witness time on a scale that dwarfs imagination. It may have left its home system tens of millions of years ago, perhaps even before the first humans walked upright. It will continue long after Earth itself has changed beyond recognition. Our entire civilization is a flicker compared to its voyage. And yet, for a few short months, our paths overlapped. That coincidence, the meeting of something that drifts for eons and a species that's only just begun to look upward, feels almost sacred. It reminds us that the universe is not static, it's a tide. Everything moving, mixing, exchanging places. Stars are born, burn and die. Planets form, crumble and scatter. Even the space between systems, which once seemed empty, is revealed to be full of motion. Most interstellar objects will never be seen. They're small, dark, invisible to any telescope. They pass through the solar system without ever reflecting a photon toward us. And yet, they're constant, tiny grains of the galaxy's circulation. In that sense, 3I Atlas is a reminder of both our progress and our limitations. We have learned to detect a handful out of countless billions. For each one we name, there are millions that remain unmarked, anonymous, forgotten before they're found. But perhaps that's part of the beauty. The fact that the galaxy is busy with unseen travellers, a quiet traffic of dust, ice and stone, gives the cosmos a kind of pulse. It means that even in stillness, everything is in motion. If you could step back far enough, beyond the Milky Way, beyond time itself, you might see it differently. Not as stars and comets, but as currents of shared matter looping endlessly through light and dark. The hydrogen that once burned in another sun now glows in ours. The dust of one world becomes the seed of another, and the same atoms that drifted through interstellar space 1 billion years ago might someday flow through oceans again, breathe through lungs again, live again. In that sense, nothing is ever lost, only transformed. Even 3I Atlas, destined to vanish into darkness, is part of that unbroken continuity. Its fragments will wander until gravity gathers them elsewhere, until sunlight warms them once more. When we speak of connection, we often mean human connection, the bonds between minds and hearts. But there's a deeper connection that precedes us and will outlast us, the unity of matter itself, the realization that every piece of the universe shares the same origin, the same story of birth and dispersal. 3i Atlas is a small symbol of that truth, a solitary object reminding us that we are, quite literally, made of the same dust. We are part of the same grand motion, the same cosmic drift. And perhaps that's what makes its passage so hauntingly beautiful. It asks us to look at ourselves not as fixed beings, but as travellers too, brief configurations of stardust passing through light before returning to the dark, just like it. Somewhere, far beyond the reach of our telescopes, 3i Atlas is still moving, its path a quiet curve through the infinite. It carries no message, no mission, no memory of being seen. But for us, the memory remains, a fleeting alignment between two journeys, one human, one eternal. It reminds us that impermanence is not emptiness, it's participation, that to exist, even briefly, even unseen, is to be part of the motion that keeps the universe alive. And maybe that's what interstellar drift really means. Not loneliness, but belonging. Not distance, but connection, carried softly through time. By now, 3i Atlas is gone. Not gone in the dramatic sense. No collision, no explosion, no final blaze. But in the quiet, inevitable way that all things drift beyond reach. It has passed the orbit of Jupiter, a faint grain of ice and dust sliding outward through the long twilight of the solar system. Its path curves gently, opening wider and wider until the sun's gravity no longer bends it. After that, it simply moves in a straight line, forever. Somewhere ahead lies the interstellar dark, the boundary where the solar wind thins into silence and our star's influence fades. Crossing that line, 3i Atlas will enter the galactic night, a region where the nearest beam of sunlight is just another star among billions. There it will cool to almost absolute zero, its last trace of warmth radiating away into the cosmic background. It won't stop moving. It will keep gliding through the void at roughly 26 kilometers per second, nearly 60,000 miles per hour. A speed that sounds fast until you measure it against eternity. At that pace, it would take more than 20,000 years just to cross a single light year, and perhaps millions to approach another star. But time means little to an object like this. It has already wandered for eons, and will wander for eons more. In its wake, it leaves only data, a scatter of numbers in observatory archives, brightness curves on computer screens, a few spectral lines etched into files. Yet those traces have changed how we see the cosmos. They've shown us that the space between stars isn't a sterile gulf, but a corridor of exchange, a highway of frozen messengers drifting quietly between suns. 3i Atlas has reminded us that our solar system is not a sealed system, but a porous frontier. Material comes and goes. The dust of our own comets escapes into interstellar space, while fragments from other stars drift in. For all our charts and boundaries, the cosmos ignores ownership. It is open, shared, continuous. In that sense, 3i Atlas is more than a visitor. It's proof of connection. It carries within it the chemistry of another star's beginning, and for a few brief months, it mingled that history with ours. Light from our sun touched it. Photons bounced from its surface and travelled back to Earth, carrying with them the signature of alien ice. That light entered our telescopes, our detectors, our eyes. For a moment, we quite literally shared sunlight with another world. What have we learned from its passing? That other planetary systems exist not only as distant points on a map, but as tangible presences, their fragments crossing our sky. That every world, no matter how remote, contributes to the same galactic story of motion and transformation. And that discovery, in its truest form, is often fleeting. a single alignment between curiosity and coincidence. 3i Atlas taught us humility too. We saw it only because we happened to be watching. Had its trajectory shifted by a fraction of a degree, it might have slipped past unnoticed, another invisible thread in the dark fabric of the galaxy. It's a reminder that knowledge depends as much on patience as on luck, that the universe will reveal its wonders, but only briefly, and only to those who are ready to look. Soon it will cross the heliopause, where the solar wind surrenders to the interstellar medium. Beyond that, the space is neither silent nor empty, but filled with an ancient murmur, faint magnetic fields, drifting atoms, cosmic rays whispering between stars. There 3i Atlas will travel on, cold and unlit, another ember among countless others. Maybe one day it will pass near another star, warming slightly as it drifts through a new sun's faint glow. Maybe that star will have its own observers, its own instruments, its own night sky. And perhaps, for a moment, they will see a tiny moving dot, a faint, unfamiliar light, and wonder where it came from. They will give it a name, chart its path, and imagine the world that once gave birth to it. They will not know that it once passed through our sky, or that we too once watched it go. But that's the quiet beauty of motion. Stories continuing where we can't follow. If we could see it now, it would be little more than a pinprick against the dark, too dim for even the largest telescopes. And yet the knowledge of its presence lingers. The idea that somewhere out there, a fragment from another star carries the memory of our sun's touch. It leaves us not with closure, but with perspective that the cosmos is full of brief intersections, moments of shared existence before distance takes over again, that every comet, every particle of dust, every human life is part of the same unending drift. So we let it go, this small guest from another sun, and watch, at least in imagination, as it fades into infinity. It becomes one with the background of stars, indistinguishable, eternal. And perhaps that's the truest ending of all, not disappearance, but return, a fragment rejoining the quiet current of creation, carrying with it a glimmer of our own light, moving forever through the endless dark.